तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were discussing about sedimentation. We have seen that sedimentation is a unit operations. It is utilizing the settling velocity of the particles to remove it from the water and clean the water. Okay. So, we can go either for settling or flotation for the removal of particles which is large enough. And we have seen, based upon the properties of the suspension, we can divide the sedimentation into different categories. Those are type 1 settling, type 2 settling, zone settling and compression settling. And in water treatment, most of the time we come across this type 1 settling and type 2 settling. Type 1 settling is for discrete dilute suspensions, and we have seen in detail what is a discrete particle. A discrete particle is the one whose size, shape, specific gravity or the properties will not change with respect to time, but a flocculent suspension is the one whose properties will change with respect to time. So, in water treatment, most of the time in primary sedimentation tank it is type 1 settling, and in coagulation flocculation, after the coagulation flocculation in clariflocculator we go for, or we have flocculent settling. And we have also seen in detail how to calculate the efficiency of a tank when it is a discrete particle settling or if it is for a flocculent particle settling, and how to conduct the settling column studies, etc. So, today we will see in detail what are the different types of sedimentation tanks and what are the important components of a sedimentation tank, and how to design a sedimentation tank, and how can we find out the efficiency of a sedimentation tank in actual practice, because theoretically we can tell that okay, we can achieve 100% efficiency and all, but in actual practice in field we will not be able to get that much of efficiency. So, we will discuss in detail what are the factors that affect the efficiency of the sedimentation process and how can we find out the efficiency, etc. in detail. So, coming to sedimentation tanks, we can have different types of sedimentation tanks, or we can classify the sedimentation tanks into different categories. The first classification is either horizontal flow sedimentation tanks or vertical flow sedimentation tanks. In horizontal flow sedimentation tanks, as the name indicates, the flow is in horizontal direction. That means water enters in one side and it flows horizontally. So, that is known as a horizontal flow sedimentation tank. And in vertical flow sedimentation tank, the water flow direction is in the vertical direction. That means water enters in the tank from the bottom portion and it comes up and it distributes. Okay, so this is very common in circular sedimentation tanks. Okay, and we can classify again the sedimentation tanks either long rectangular tanks or square tanks or circular tanks. So, we will see those in details. First, we will talk about long rectangular basins. Okay, these are the best basins as far as hydraulics is concerned, because these basins are hydraulically more stable, and moreover flow control is very easy in such basins. And in long rectangular basins, usually the length is 2 to 4 times and sometimes even 5 times the width of the tank. Okay, this is important. The length is around 2 to 3, 2 to 4 or sometimes even 5 times the width of the tank, or 10 to 20 times the height of the tank is equal to the length of the tank. Okay, so these are the parameters, and in this case the bottom is slightly sloped. Okay, the reason for this one is if you want to remove the settled sludge, okay, it is very easy if you provide a slope in the bottom. So, the bottom is slightly sloped and usually the slope is around 1%, and the sludge removal is carried out by using a slow moving mechanical scraper, and redwood pieces on a chain drive continuously pulls the settled material, and all the settled material will be coming to a particular portion, and from there we can pump it out. Okay, so that is what is happening. And in the sludge hopper, whatever the sludge accumulated, it is pumped out periodically. So this is the properties of a long rectangular basin, and the most important one is hydraulically it is more stable, and we will see what all are the advantages of this long rectangular basin afterwards. The most important one is it provides a plug flow, and plug flow is very, very important to get maximum efficiency. So this shows the sketch of a sedimentation tank, a rectangular sedimentation tank. So this is the inlet zone. The water to be treated is entering here, and this is the baffles. Okay, that inlet pipe should be facing a baffle, and this baffle is having many openings. So we can see that these openings. Okay, and this is the settling zone of the sedimentation tank. Okay, whatever we are designing. Okay, so this is the portion we are designing. This is the settling zone, and this is the sludge scraper. We can see that. Okay, it is connected in the pulleys, and these are the scrapers. So this is the wood scrapers. So what will happen? Okay, motor is attached to this one. So this will be moving in this direction. So what will happen? Whatever is the sludge settled in the bottom of the sedimentation tank. Okay, here all the things will be scrapped, and this is the sludge hopper. So everything will be coming here, and it will be pumped out using a pump. And this is the outlet zone. Okay, outlet zone is designed in such a way that minimum disturbance will be provided for the settled sludge. If the turbulence is more here in the outlet zone, what will happen? Whatever the sludge settled in the bottom of the sedimentation tank will be getting disturbed, and the particles will be escaping through the treated water in the effluent. So we will not be getting the required treatment efficiency. So outlet zone should be designed properly to get or to achieve proper efficiency or to achieve the required effluent quality. So once again, the important parts of a sedimentation tank are: first one is the inlet zone, second one is the settling zone, and then the outlet zone, then the sludge zone and sludge removal mechanism. Now we will see in detail what are the purpose. Okay, this is another picture which is showing a circular sedimentation tank. Okay, earlier one was a rectangular sedimentation tank. This is a circular sedimentation tank with peripheral feeding. So the inlet is here. Okay, we can see that the water is coming here, and it is taking a path like this, and this is the effluent collection weirs. So this portion will be acting as the settling zone. Similarly here also, this is the inlet zone. Okay, the water takes a path like this. During this period, whatever is the particles present in the water will be settling down, and the clear water will be collected here. This is the effluent collection weir. Okay, this one, and here the slope is this direction. So whatever is the sludge settled in the bottom of the tank, everything will be coming here, and from here it is taking away. So this is the way a circular tank with peripheral feed is working. And this is again another example. Here the outlet weir is situated in the center. Okay, in the previous case we have seen that the weir is also in the periphery. Okay, and inlet and outlet both are in the periphery, located in the periphery. In this case, the inlet is in the periphery, the outlet is in the center. So the water will be taking this type of a path, and here we are providing a baffle wall, okay, in order to reduce the kinetic energy of the incoming water. Otherwise what will happen? The turbulence will be very, very high, and that will be affecting the settling process. So we will not be getting much removal. And here also whatever is settling here, everything will be coming to this portion, and from here the sludge will be taking away. So, I have already discussed that the sedimentation tank will be having various zones. The first one is inlet zone, then the settling zone, outlet zone and the sludge zone. The inlet zone, the major purpose is, or in the inlet zone in which the baffles intercept the incoming water and spread the flow uniformly, or the major purpose of the inlet zone are, the first one is uniformly distribute the incoming flow, because incoming pipe will be only one and you will be having so much of width for the sedimentation tank. So, we have to distribute the flow uniformly throughout the sedimentation tank, then only the entire area or entire volume of the sedimentation tank will be effectively utilized. So, that is the most important purpose of the inlet zone, okay, distributing the flow uniformly throughout the tank. And second one is to minimize the turbulence created by the incoming flow, because we know that the water will be entering in the sedimentation tank with a high velocity. So, if we allow that one to enter in the settling zone with the same velocity, what will happen? It will be creating lot of turbulence in the sedimentation tank. If the turbulence is more, what will happen? Whatever the sludge settled in the bottom of the tank, it will be coming out. So, we have to design the inlet zone in such a way that the turbulence should be minimum. And the third purpose is to train the flow, okay, so that it will be equally distributing and it will be uniformly flowing throughout the sedimentation tank. So, these are the purposes of inlet zone. So, always the inlet pipe will be facing a baffle which will be reducing the kinetic energy of the incoming water. Then this baffles will be having many ports on that one or many holes on the baffle wall. So, this walls or this ports, what will happen? The water will be uniformly escaping through the ports to the settling zone, and when water enters the ports, what will happen? There will be a head loss, and the ports are designed in such a way that the velocity through the ports should be around 0.2 to 0.3 meter per second, and the head loss through the ports will be around 1.7 times the velocity head. Okay. So, these are the important things we have to consider when we design the inlet zone. So, once again, the inlet pipe should be faced to a baffle wall to dissipate the kinetic energy of the incoming wall, and most of the time the inlet zone will be made in such a way that the baffle wall will be having many ports or many holes, and the water will be coming into the inlet zone, and from the inlet zone through these holes of the baffles it will be entering into the settling zone. So, these walls, the ports in the baffle walls will be distributing the water equally to the inlet zone. Moreover, it will be reducing the kinetic energy, because there will be lot of head loss when the water passes through the holes. And in the outlet zone, what is happening? The water flows upward and over the outlet weir. So, it will be reducing the turbulence and it will be improving the quality of the treated water. And in the sludge zone, okay, which extends from the bottom of the tank to just above the scraper mechanism, this is the sludge zone, and the last one is the settling zone, okay, which is responsible for the settling process. So, in settling zone, in the inlet zone, the opening must face a baffle. This I have already explained, and we have seen the purpose. The purpose of this one is to dissipate the kinetic energy. I will show you some of the inlet arrangements. So, this is one of the inlet arrangements. So, here the influent pipe is coming, okay, and this is the inlet of the sedimentation tank, and this is the baffle. Okay. Here we can see that openings, multiple openings, okay, and this baffle wall goes up to the bottom of the tank, and what will happen? The influent pipe brings the water here and the water will be stored here, and from here the water will be going to the settling zone of the sedimentation tank. Okay. This portion will be the settling zone, okay, through this multiple openings. So, what will happen? The velocity of the incoming water will be reduced and the water will be equally distributed throughout the width and depth of the tank. So, the settling zone will be completely utilized if you give this type of an arrangement for the inlet. And this is another type of inlet arrangement. So here what is happening, this is the inlet pipe, okay, and here we have an orifice, submerged orifice. So the inlet pipe brings the water here, from here it is passing through this orifice, and this orifice will be having multiple openings because this is only a portion, and throughout the cross section we can see many openings, and afterwards to reduce the kinetic energy further we provide a baffle wall. Okay. So you will be having uniform distribution of the water because of this multiple openings, and because of the baffle wall the turbulence will be reduced or minimize the turbulence to the possible extent. And this is another type of an inlet arrangement, it is influent channel with bottom openings. So here what is happening, the water is coming through this pipe, and this is your storage place, okay, and it will be having a bottom opening. So what will happen, the water enters here like this, and the direction will be changed, and it will be coming to the settling zone like this. Here also multiple openings will be there throughout the width of the tank. So there will be some uniform distribution of the water as well as, okay, energy destruction. And this is another type of an inlet arrangement, which is an overflow weir followed by a baffle. Okay, here we have seen a submerged orifice, okay, here overflow weir. So inlet pipe is here, whatever is the water coming, it will be overflowing through this weir, and here a baffle wall is there, okay, and afterwards the water will be going to the settling zone. So all these things are meeting the basic requirements, that is uniform distribution of the water as well as minimizing the turbulence and training the flow in the settling zone. Okay. So these are the purposes of the inlet, and these are the commonly used inlet arrangements in a sedimentation tank. So whenever we design a sedimentation tank, it is very important to design properly the inlet zone, outlet zone and sludge zone. Anyway, we will be designing the settling zone properly based upon the principles whatever we have seen earlier. Now we will see, okay, how the outlet zones are designed in a sedimentation tank. Okay. Most of the time the outlet zone consists of a launder and an outlet pipe. Okay. It consists of V notches attached to single or both sides of single or multiple troughs. Okay. So this I will explain in detail when we do the design problem. And most of the time what will happen, the center to center distance of this V notch will be around 150 to 300 mm. Okay. So in the outlet zone trough many V notches will be there, and this V notches will be placed a center to center distance of 150 to 300 millimeters. And just before the outlet zone there will be a baffle. We have seen that in the inlet zone, after the inlet pipe we will be providing a baffle, but in the outlet zone what is happening, the baffle will be provided first, then the outlet launder or the V notches will be coming. The purpose of this baffle is to prevent floating matter from escaping into the effluent, because there will be many floating materials as well as scum in the sedimentation tank, because if the whatever is entering in the sedimentation tank is having oil or grease or any floating material, it will not be removed by settling. So that definitely it will be present in the surface of the sedimentation tank. So definitely if we want to provide any obstruction, it will be coming and escaping through the effluent. So naturally the effluent quality will be destroyed or effluent quality will be spoiled. So if you want to improve the effluent quality, we have to remove the scum as well as the floating matter from the sedimentation tank. So these baffles whatever is provided in the outlet zone is serving that purpose. Okay. And another important factor which we have to consider when we design a outlet zone is the weir loading rate. Okay. If we go for a high weir loading rate, that means the rate at which the water escaping through the weir is very high, then what will happen? Definitely the turbulence will be very high. So that will be destroying or that will be reducing the efficiency of the tank. So weir length relative to the surface area determines the strength of the outlet current. So this point is very important. The weir length is the one which decides the strength of the outlet current. To get maximum efficiency, we have to keep the strength the minimum possible. So usually whenever we design a sedimentation tank, the weir loading rate, okay, we usually keep it at this value 300 meter cube per day per meter. But if the settling is very good, then we can go for a higher weir loading rate up to 1500 meter cube per day per meter. But usually we keep a value of 300 meter cube per day per meter. And how can we find out the weir loading rate? It is nothing but the flow rate divided by the weir length. So what is the flow rate per weir length? That will be giving you the weir loading rate. That is why this unit is coming, because your flow rate unit is meter cube per day, okay, that which is the flow entering in the sedimentation tank, and your weir length will be given in terms of meter. So weir loading rate will be in terms of meter cube per day per meter or meter cube per hour per meter. So these are typical outlet arrangements. So we can see here, this is the baffle whatever we were discussing earlier. So this baffle will be preventing all the floating materials and scum materials to escape into the outlet zone. Okay, from here, okay, this is the treated effluent, okay, this is the V notches. We can see many V notches, and the center to center distance between these two V notches is usually 15 to 30 centimeters. So the water, whatever is treated water, it will be escaping through this to the effluent launder through the V notches, and from here it will be going to the effluent box, and from the effluent box it will be collected through the effluent pipe. So an outlet zone consists of many V notches, okay, which collects the water to the effluent launder. From there it is going to the effluent box. From the effluent box, the treated water is collected through the effluent pipe. Okay, this is another type of an effluent outlet zone. This is consists of outlet with rectangular weir. Okay, so here we are having a weir. Okay, before this one we will be having a baffle wall to remove the floating as well as floating materials as well as scum, and the treated water is coming here, which is free from floating matter and scum, and it is passing through this weir. Okay, most of the time this weir length is adjustable, and this is escaping here, and this is known as the outlet flume, and from here the treated water is collected through this outlet pipe. Okay, so these are very important. So whenever we design a sedimentation tank, we have to design the inlet zone and outlet zone properly. Okay, so this is a sedimentation tank with all the details. Okay, this is the influent inlet arrangement. Okay, so influent is coming here, and this is the baffle. Okay, so here it is coming here, and this is the settling zone, and we have the sludge scraper mechanism here. And this is another important point. Most of the time the sludge hopper will be situated near the inlet zone. The reason is, okay, if you provide the sludge hopper here near the outlet zone, if the turbulence is more here, okay, it is easy to get disturbed whatever the sludge present here in the sludge hopper, and it can escape through the effluent or outlet arrangement. So it is always advisable to keep the sludge hopper in the inlet zone, so that the disturbance will be the least and we will be getting a better effluent quality. Okay. So this is the inlet zone, and this is the settling zone, this is the sludge zone, sludge scraper, sludge hopper, and this is the outlet. Okay. So we are getting the outlet effluent from here. Okay. Here an adjustable weir is used as the outlet arrangement, and this is another type of outlet arrangement. So here what is happening is, okay, this is a weir and we are collecting the effluent here, and from here whatever is collected, okay, finally everything is coming out through this one, and here we can see the sludge scraper is little different from the one whatever we have seen here. Okay. So we can provide any type of sludge scraper, but only thing is, okay, it should be able to remove the collected sludge effectively, and we should provide proper sludge removing mechanisms. Okay, we should not allow the sludge to accumulate here in the sludge hopper. So, the pump should be operating periodically to remove the sludge whatever is collected in the sludge hopper. So, another important factor whenever we discuss about the sedimentation tank is surface loadings and detention periods, and we have seen what is this surface loadings in the last class. Okay. So, the removal of a particle, okay, we have seen that the time required for the removal of a particle is depending upon the settling velocity, and we have seen how to calculate the settling velocity in case of a discrete particle. Okay, we can use the Stokes law to find out the settling velocity, and in flocculent particles it is we cannot use the Stokes law. The reason is the particle size, shape and the properties will be changing with respect to time, and we have seen that the settling velocity of the discrete particle will be increasing with respect to time. The reason is more and more particles will be agglomerating together with respect to time. So, as the particle size increases, the settling velocity also will increase. So, removal of a particle is directly proportional to the settling velocity, and we have seen that the settling velocity of a particle in the sedimentation tank is numerically equal to the surface loading or surface loading rate, or the removal of a particle is a function of surface loading or surface loading rate. Okay. So, I will show you how to derive this one. Okay. This is very important when we talk about high rate reactors also. So, the settling velocity is nothing but V naught. V naught is h by t. Okay. H is nothing but the height of the tank and t is the settling time. Settling time. Okay. So, this we have seen. Okay. If we have a tank, okay, this is having a height of h, okay, and here one particle is there, it is settling with a settling velocity of V naught, okay, and or we have a particle, it took around t seconds or t minutes to reach the bottom of the tank, then we can find out what is the settling velocity. So, the particle removal is a function of the settling velocity, and we have seen now the settling velocity or the particle removal is a function of surface loading, surface loading rate. Surface loading rate is nothing but this is the flow rate divided by surface area. How to show this one? Okay, we will see that one. Okay, we have this expression V naught, the settling velocity is equal to h by t, and we have the sedimentation tank with a volume. Okay, any sedimentation tank volume we can find out by multiplying length of the sedimentation tank by width by height. Okay, so this is the volume of the sedimentation tank, and if you want to find out the height of the sedimentation tank, what is that one? Volume divided by surface area. Okay, that will be giving you the height. Okay, so what is the surface area? Surface area is nothing but length into width. So we can write like this. Okay, so here we are finding out what is the height of the or depth of the sedimentation tank if you know the volume of the sedimentation tank and surface area. Okay, so volume of the sedimentation tank is nothing but length into width into height, and surface area is length into width. Okay, so that is the surface area. So you will be getting height. Okay, and we have seen that V naught is nothing but h by t. So we have the h value like this, that means volume divided by surface area and t. Okay, so if you talk about a sedimentation tank, what is the t or what is the time the water or any particle that is getting in the tank, that is nothing but volume of the tank divided by the flow rate. Okay, this is nothing but the hydraulic retention time. Okay, so this is the time the particle is getting inside the tank, that means volume. So we have a particular volume and we know the flow rate, so we can find out what is the time that water is going to stay inside the tank. So we can put this one. Okay, so this expression we can write like this: V naught equal to H by T, so that is equal to L into V into H divided by L into B. So that will be giving you the H value. Now T is nothing but volume by Q. So this volume we can again replace by L into B into H. This is nothing but the volume of the sedimentation tank. So what will happen? These terms will be getting cancelled and you will be getting Q divided by L into B. So this is nothing but Q divided by surface area. So that is what we have seen in a sedimentation tank. The settling velocity or the removal of the particle or particle removal efficiency is a function of surface overflow rate. Surface overflow rate is nothing but the flow rate divided by the surface area. So that is the surface overflow rate, and the particle removal is independent of the height of the tank or H. Okay, this is very important when we talk about the high rate sedimentation tanks, that we will discuss in detail towards the end of the class. So we have seen that the removal of a particle is a function of surface loading or surface loading rate, and usually in a sedimentation tank we provide a depth of 2.5 meter to 3 meters in case of discrete particles, and flocculent particle we usually give 3 to 4 meter. Okay, though we have seen that the depth of the tank is not an important factor, what will happen if the depth is too minimum, whatever the sludge settled on the bottom of the tank will be coming out because of the turbulence. So that is why we are providing a depth of 2.5 to 3 meter. In case of flocculent particles, what will happen, as the particles travel downward direction, with respect to time the particle size will be increasing. So if you provide large depth, the removal efficiency will be high, and usually the width of the tank is 12 meters. Otherwise the sludge removal is a problem, because to fix the sludge removal mechanism, okay, it is always advisable to provide a width of 12 meters or more, and length of the tank varies from 10 to 48 meters, and the settling velocity of the particle, if it is discrete, it varies from 1 to 2.5 meter per hour, and for flocculent particles the settling velocity varies from 0.6 to 1 meter per hour, and these are the typical surface loading rates and detention periods for various types of sedimentation tanks. For a plain sedimentation tank, that means there is no coagulation, flocculation, and most of the particles are discrete in nature. So the range is 0 to 6000, but typical values for design is 15 to 30 meter cube per day. So this is the surface loading rate usually we provide, and for horizontal flow circular sedimentation tanks, the typical values for design is 30 to 40. This is for rectangular 15 to 30 and circular 30 to 40. And vertical flow clarifiers, here the flow direction is in the opposite, from the bottom to the top most of the time. So in such cases we can provide a surface loading rate of 40 to 50 meter cube per day, and for plain sedimentation we can give a detention period of 3 to 4 hours if the particles are sand, silt and clay, and for horizontal flow circular sedimentation tanks the detention period can be 2 to 2.5 hours, and vertical flow usually a detention time of 1 to 1.5 hours is provided. Now we will see how to design a long rectangular settling basin for type 2 settling. Type 2 settling means it is flocculant particle settling. So, this is the problem. A city must treat around 20,000 meter cube per day of water. Flocculating particles are produced by coagulation, and a column analysis indicates that an overflow rate of 20 meter cube per day per meter squared will produce satisfactory removal at a depth of 3.5 meter. Design a sedimentation tank. So, we will see what are the informations are available. We have the Q, okay, the flow rate 20,000 meter cube per day, and we have the surface loading rate, that means this much meter cube per meter squared per day, and the depth of the tank is also given 3.5 meter. So, we will see how to design the tank. First we have to find out what is the surface area required, because we know the depth of the tank. So, how can we find out the surface area? So, we know that we have the flow rate and we are providing 2 tanks because the flow rate is very high. So, we are providing 2 tanks. Each tank will be taking care of 10,000 meter cube per day. So, the Q is 10,000 meter cube per day, and this is equal to Q naught into AS, where AS is the surface area and this Q naught is nothing but the surface overflow rate. So, surface overflow rate is already given as 20 meter cube per meter squared per day. So, we can find out what is the area required. So, just divide this one by the surface overflow rate. So, we will be getting 500 meter squared. Now, we have to find out how much is the length and width we have to provide. So, we are assuming the length to width ratio as 3:1. So, we have seen that we can provide 2 to 5. The length of the tank is around 2 to 5 times the width of the tank. So, we are assuming 3 times. So, we can find out the width like this, W into 3W, that means this is the L as 500 meter squared. So, width is coming as 12.9 meter. So, either we can go for 13 meter or 14 meter. So, I have taken 13.5 meter because we have to satisfy other conditions. So, the length will be around 3 times this one. So, we are providing a length of 40 meters. Now, we have to check for the retention time. So, how to find out the retention time? It is nothing but V by Q. So, that is the retention time. So, we can find out what is the volume because we know the width, we know the length, we know the height. So, this is the volume divided by the flow rate. So, it is coming around 0.189 days or 4.5 hours. So, we have seen that in the discrete settling we can go up to 4 hours. Okay, this is higher than that. So, it is safe. Now, we will check for the horizontal velocity because if the horizontal velocity is high, more turbulence will be generated and that will be affecting the efficiency of the system. So, the horizontal flow velocity is nothing but Q divided by the cross sectional area. So, that we can find out using this expression 10,000 divided by width and depth. So, you are getting 8.82 meter per hour, and for discrete particles it should be less than 9 meter per hour. So, it is satisfying that condition. And now we have to see the weir overflow rate. So, the weir overflow rate should be less than 300 meter cube per meter square per hour. So, here we are getting around 30.8 meter cube per hour per meter, and this is not satisfying that condition. So, how can we achieve the condition? So, what we can do is, okay, instead of providing only one layer of weir, in the end we can provide multiple weirs. Okay, I will show you. So, this is your sedimentation tank. Okay, sedimentation tank, and this is your inlet and this is your outlet and this is the settling zone. So, usually what we give is we will be having a weir here and this is the outlet zone. So, instead of providing one weir here, so what we can do is we can provide multiple weirs. So, like something like this. Okay. So, water will be coming to this one from both sides like this, and this ones we can connect through a pipe, something like this. So whatever water collected, it will be entering here and it will be going to the outlet pipe. So instead of providing a single row of or single weir length, we can provide 2 or 3 weirs here. So that will be taking care of the weir loading rate. So this is what usually we provide in the rectangular tanks. But when we talk about the circular tanks, this weir loading rate will not be a problem, because in circular tanks what will happen, this is the cross section of a circular tank. So the inlet will be most of the time in the center, so it will be coming like this. So this is the outlet. So entire periphery of the tank will be available for this weir. So the weir loading rate will not be a problem in circular tanks, but in rectangular tanks, if you provide only one line of weirs, it may not be meeting the weir loading rate. So in such cases we have to provide parallel weirs. So this point is very, very important. So if you want to draw the picture, whatever we have designed so far, it comes like this. So whatever dimension we have got, that 40 by 13.5, that is for the settling zone, and we have to provide the inlet zone, we have to provide the outlet zone depending upon the weir loading rate, and we have to provide the sludge zone. Usually we provide a slope of 1%, and this is the sludge hopper which is situated in the inlet zone. And the total height of the tank will be coming around 4.5 meter. The reason is 3.5 is the depth of the settling zone, and we have to provide around 0.5 meter for the sludge zone and 0.5 meter as the freeboard. So that is why it is coming as 4.5 meter. And in circular basins, the flow regimes are different from rectangular basins. Okay, in most of the cases, the flow direction is from the center to radially towards the perimeter. And here what is happening is, the horizontal velocity will not be a constant, it will be decreases, it decreases as the distance increases from the center. The reason is, if you take any section, the cross sectional area will be increasing as we go towards the perimeter of the circle. So that is why, okay, the horizontal velocity will be keep on decreasing. So you will not be getting a linear velocity change, it will be in parabolic. Okay. So V0 is not a constant, it will be continuously changing, and if you find out the particle path, it will be following a parabola. And here if you go for circular tanks, the major advantages are sludge removal mechanism is simpler, and weir of overflow rate, as I have already mentioned, it will not be a problem because entire perimeter is available for the weir. And usually when we go for tanks in circular shape, okay, the D should be less than 30 meter. Okay, it is easy for construction and all those purpose. That is why we are restricting the diameter as 30 meter. So this is the same problem if you design a circular settling basin. So here what I have done is, I have taken 3 tanks instead of 2 tanks. So we will be getting the same way the cross sectional area as 333.33 meter squared. So we can find out what is the diameter. The diameter is coming as 20.6 meters, or we can provide as 22 meters. So and it also should have the inlet arrangements and outlet arrangements and sludge collection systems. So if you want to give the dimensions, so this is the settling zone, okay, and this is the inlet zone and this is the outlet zone. So if you provide the inlet zone and outlet zone along with the settling zone, then you will be getting a total diameter of 34 meter, though the inlet zone itself requires only 22 meters. So just now we were discussing about the discrete particle settling, and we have seen that the depth of the tank is not very important in discrete particle settling. Based upon this principle, okay, high rate sedimentation tanks are being designed. Okay, tube settlers or inclined plate settlers are examples of high rate settlers. So here what we are doing is, we are providing excess surface so that the surface overflow rate will be decreased. Okay, so we have a sedimentation tank like this, say some 3.5 meters depth. So if you provide many plates parallelly in the settling zone. So what will happen? The effective surface area will be increasing because many surfaces are available for the settling or many planes are available for the settling. So effectively what will happen? It will be considerably reducing the surface overflow rate, or in other words it will be increasing the efficiency of the tank. So that is the principle of these tube settlers. And here, okay, the design is based upon the surface overflow rate. So here we are providing many tubes or inclined plates at an angle of 45 to 60 degree above the horizontal. Okay, why we are providing this 45 to 60 degree angle is, okay, because the particles will be settling on the plates or the tubes. So if you provide an angle 45 to 60 degree, so what will happen? Whatever the particles settled on the tubes or the plates, it will be sliding back to the system with the self weight. So cleaning will be very easy. So people have shown that if you provide an angle of 45 to 60 degree, the efficiency of the system will be maximum. And in such cases, the spacing of the plates will be around 5 centimeter and length of the plates will be around 1 to 2 meters. And when we talk about this tube settlers, okay, it can work in 3 different modes, either counter current mode or co-current mode or cross flow. So this shows how the 3 systems are functioning. This is an example of counter current mode. So here what is happening? The plates or the tubes are placed at an angle theta degree to the horizontal and it is an inclined plate. So what will happen? The liquid will be entering through the plate like this. So if it is a tube, what will happen? The water or the particle will be going and touching the top portion of the tube and afterwards it will be coming down and it will be getting settled. And if it is a plate, okay, the same thing will be happening. So what will happen? Here the liquid flow is in this direction. Okay, we can see that the velocity V0 is going in this direction and particle settling will be in the opposite direction. Okay, it will be settling and particle will be coming back to the system because the plates are inclined like this. So that is what is known as counter current. That means the flow is in one direction and particle settling and removal is in the opposite direction. So that's why it is known as counter current. And this is co-current. Co-current, what is happening? This is the liquid flow direction and this is the solid removal direction. So both are in the same direction. That means the water is entering like this and as it enters and the particles will be following this trajectory and it will be coming and settling here and it will be getting removed and clear water will be going like this. So both are in the same direction. This is co-current and this is cross flow. That means here the flow is in this direction. The plates are placed parallelly and flow is in this direction and solids will be settling in this direction. So that is why it is known as cross flow. Okay, this is a typical cross section of a tube settler, plate settler. Here we can see many plates are provided. So all these things are plates. Okay, and this is a coagulation, flocculation and clarification. So this is the flocculation tank and from here the water is coming here and this is the underflow sludge. The water flow direction is like this, you can see that one. Okay, and as it comes here we will be getting the clear water and this is the overflow box and from here, okay, we can see that the clear effluent is collected. Okay, and this is the feed box and whatever is the sludge collected, okay, this is the sludge hopper and from here the sludge is collected through this pipe. Okay, so this is how a tube settler is functioning. So we are having many parallel plates. So here what we are doing is by utilizing a small area we are increasing the efficiency of the tank. Okay, so that is the major principle of tube settlers. So in counter current settling, how can we find out the time required? The time required is nothing but what is the time taken by the particle to travel the perpendicular distance between the plates. So that is nothing but W by V cos theta. This is the velocity component. Okay, T is the time for a particle to settle the vertical distance between two inclined plates and W is the perpendicular distance between the plates and V is the velocity and theta is the angle of the surface inclination from the horizontal. And similarly, we can find out what is the length of the plate required. It is equal to W into V naught minus V sin theta by V cos theta, where LP is the length of the plate or length of the surface, and V naught is the liquid velocity between the surfaces, and N is the number of plates, B is the dimension of the surface perpendicular to W and Q. Okay, and we can find out what is the V theta. It is equal to Q, the flow rate, divided by number of plates divided by, this is the perpendicular distance and this is the width. So, cross sectional area, flow rate divided by the total cross sectional area will be giving you the velocity. In co-current also similarly we can find out what is the length of the plate, that is equal to W by V naught minus V sin theta by V cos theta, and V is equal to the settling velocity should be greater than or equal to V theta into W by LP cos theta minus W sin theta. So, these things we can get by just analyzing the velocity components. Okay, it is nothing difficult. And in cross flow settling, the length of the plate required is W V0 by V cos theta, where V0 is the flow velocity and settling velocity should be greater than or equal to V theta into W by LP cos theta. So, depending upon the flow regime or depending upon the arrangement, the length of the plate required and the settling velocity will be varying. Now, till now we were discussing about the settling tank efficiency, okay, theoretically, but in practical condition the settling tank efficiency will be varying because of the inertia of the flow, okay, because always the flow will be having a tendency, or the particles will be having a tendency to continue the same flow regime. Okay, so that is the inertia. Second one is the wind effect. Third one is because of the turbulence created in the system and because of the temperature variations. All these things affect the efficiency of the tank. So, we will see one by one in detail. Okay, the factors that affect the efficiency are inertia of the incoming water, because the water will be having always a tendency to follow the same condition. The second one is wind effect. Third one is because of the turbulence, though we are trying to minimize the turbulence, okay, there will be still some turbulence, because of that one the efficiency will be reducing. The last one is density and temperature gradients. So, how the temperature gradients affect the flow conditions? Now we will take two cases. For example, you have a sedimentation tank. The sedimentation tank water temperature is higher than the influent water. So, what will happen? Though the water is getting distributed equally in the inlet zone, what will happen? Since the density of the water, whatever is present in the sedimentation tank is less compared to the incoming water, so incoming water will be always flowing to the bottom of the tank. So, what will happen? Your settling zone will not be effectively utilized. So, that is happening during summer times, but in winter times what will happen? Okay, if we are having an open sedimentation tank, the sedimentation tank temperature will be lower, so naturally the density of the water will be more, but if the incoming water temperature is more compared to the existing water, the water will be flowing in the top portion of the tank and the bottom portion of the tank will not be utilized completely. So, we will not be getting a complete plug flow regime in the sedimentation tank. So, naturally if the settling zone is not completely utilized, so definitely your efficiency will be decreasing. Similarly, the wind effect, because most of the time you will be having a wide rectangular tank as the sedimentation tank. So, if the tank length is larger, then what will happen? The wind effect will be there. So, because of the wind effect, what will happen? There will be turbulence in the top portion of the tank. Because of the turbulence, what will happen? Your settling will not be proper, okay, because for settling quiescent condition is a must. So, if lot of turbulence is there, okay, the settling efficiency will be decreasing. So, these are the factors which is affecting the sedimentation tank efficiency. So, if you want to find out what is the actual efficiency, we can conduct tracer studies. So, what we are doing in a tracer study, we are injecting a color, we are injecting a dye or some chemicals which can be analyzed easily. So, we find out the concentration of the dye or the chemical at the effluent with respect to time, and we can plot the concentrations, and from that one we can find out okay, what is the flow regime in the sedimentation tank and how much is the tank volume utilized and what is the dead volume in the tank, and based upon that one we can find out the efficiency of the system. So, this is a formula usually we use to find out the efficiency of the tank, that is equal to Y by Y naught, which is equal to 1 minus 1 plus N into V naught by Q by A raised to 1 by N. Okay, once again the efficiency of the tank is Y by Y naught, which is equal to 1 minus 1 plus N into V naught by Q by A raised to 1 by N, where Y by Y naught is efficiency of removal of suspended particles, N a coefficient that identifies the basin performance, and V naught is the surface overflow rate for ideal settling basin, and Q by A is the required surface overflow rate for a real basin to achieve an efficiency of Y by Y naught for a given basin performance. So, this formula is very important, and we will see how to find out this N value. Okay. So, we can, for finding out this N value or to determine the short circuiting, we can go for tracer study, okay, and we can make the frequency distribution chart from the model, median and mean flow through periods. We can find out the central tendency of the time concentration distribution, okay, and using this one we can find out what is the efficiency of the tank, and a well designed tank usually give an efficiency of 70%, and if it is a complete plug flow regime, that means a very narrow long tank will be getting maximum efficiency. So, this shows the tracer study, okay. Here we are plotting the relative concentration with respect to time. If it is a plug flow regime, we will be getting the concentration like this, and if it is a completely mixed tank, we will be getting a flow regime like this. So, most of the time the sedimentation tanks will be in between a CSTR and a plug flow regime. So, as it close to the CS plug flow, we will be getting more efficiency. So, it is the best one, it is almost approaching a plug flow regime, okay. B is more close to CSTR, C is less, then D is approaching plug flow, and E is almost a plug flow. So, for best possible the N value is 0, that means it is ideal, and very good performance the N value is 1 by 8, good performance it is 1 by 4, average performance it is half, and very poor performance it is 1. 1 means it is a completely sterile, it is almost acting as a CSTR reactor. So, we will see what all are the things we have discussed today. We have seen what all are the important components of a sedimentation tank. Those are inlet zone, outlet zone, sludge zone and the settling zone, and we have seen in detail how to design the inlet zone, outlet zone and the settling zone. And we have seen about high rate reactors, that means the tube settlers or plate settlers, okay, which will be increasing the efficiency of the settling. And we have also seen that in ideal case we may be able to get 100% efficiency, but in actual case the efficiency will be less.